This conference will now be recorded.
Good morning and welcome to the Mirabilis Design webinar on creating a digital twin for product definition and design. I'm your host, Deepak Shankar, and today I will be talking about the concept of digital twin and how it has helped products in a variety of market segments ranging from industrial design to aerospace, and how the product definition has been improved in terms of quality and accuracy by following the new methodology called digital twin. According to Gartner Group, digital twin is expected to be almost a de facto standard come 2022. So there's a lot of work going on in industry to adopt the digital twin concept and try to incorporate it into almost everybody's product development flow. I'm one of the founders of Mirabilis Design, and I have been involved with a variety of digital twins, virtual prototyping, system level modeling for over 20 years. A quick introduction to what is digital twin. Being a new concept, I thought it might be a good thing to bring it up. The goal of digital twin is to ensure there are no surprises during integration. So it's a virtual representation or a virtual prototype of your system before you go construct it. The main purpose of the virtual twin or the digital twin is to be able to do any timing related visualization and analysis of your particular system. Why would you want to do it? Probably the biggest reason that you want to do it is you want to get an accurate and highly verified product specification, and you'll be able to visualize the system before you go to implement. All of these really help you in identifying bottlenecks, identifying what are going to be the corner cases, identifying the potential problems with your topology, things like that, and allows you to eliminate all the possible errors before you start development. Now, before we get started on going into all the details of digital twin, I'll just bring up one example that will give you an idea of how the digital twin works. Though what you have here is an unmanned aerial vehicle, and here what you're looking at is really the three parts. The first part is the test case, which is the combination of ascent, cruise, descent, loiter, and ISR, while then you have the actual block diagram that describes the system, which in this case happens to be the UAV. So you got your hardware, software, the power systems, the RF, the GPS sensor, the thermal subsystem. So you got a variety of modules that represent the overall UAV, and this one determines what is the sequence of events that occurs within these blocks based on the activity that's listed here in the test case. Now, what you do in a digital twin is you create a prototype of this system, you run these test cases against the prototype, and then evaluate all the different metrics of interest. Can be latency metrics, can be power consumption metrics, can be budget link metrics, cost, weight, any of those kind of attributes. Before we go too deep, I'm going to just show you what a model of this type would look like. I think the model was not open. Let me go ahead and open the model for us to view. There we go. So this is the Visual Sim modeling environment, allows you to create the digital twin. You have a series of libraries on the left-hand side. You drag components out of the libraries to describe your behavior, your resources, power, traffic, use cases. And then you get a model that looks like this. If you notice here, this is a trigger, which is the use case. And these are all the subsystems, the avionics, engine, propulsion, payload, power systems, all the different subsystems right over here. What I'm going to do is I'm going to first go ahead and click on the Go button. And we're going to see a variety of statistics that are going to pop up. Right here, for example, is the latency by state. By state meaning the ascent, cruise, loiter, and ISR. You can see how much time it took in each one of those states. So you can notice that it's pretty constant in this particular design. You can also take things like what's a link margin for the RF signal, what is the power consumption. In this case, it lists out all the different devices in the system and shows you what is the power for each one, shows you what's the printout of the sensor data. So what it allows you to do is allows you to visualize your entire system based on a timing-based digital twin model that you can then utilize for for coming up with your specification, coming up with what your requirements are, looking at your feasibility, things like that. For example, this is the RF power that is being produced for this particular design. Now, one of the things that's unique with the digital twin modeling in Visual Sim is that the current methodology that you use for implementing, which is your domain level tools, remain unchanged. It's just that you're adding a layer on top called Visual Sim digital twin technology. And this particular layer is where you can run a variety of these experiments before you hand it off to the respective development tools that can go ahead and start implementing. So this one here is how an engineering organization would take advantage of a digital twin. Now let's look at how the overall project would take advantage of a digital twin. We're looking here at a future airborne capabilities environment, or what they call FACE. What the Visual Sim digital twin allows you to do is essentially allows you to create a test bed. The main goal is to check for compliance, but also to see if we can lower the implementation cost. Almost all of today's systems are electrical electronics, which means there's a huge amount of software that controls these systems. Now, software quality in general is extremely good. The problem occurs when the specification hasn't been fully thought out and there's limits in the specification, and as a result of that, you have failures. So really what this one does is focuses on the architecture of the software, what is the specification. Of course, there are other things that the project would do is trying, for example, to come up with a standard interface to connect all the subsystems, looking at your basic attributes of what's the overall power of performance for a variety of vendors that are providing data. The biggest thing, of course, of the test bed is really the innovation platform. So what happens if I add artificial intelligence? What happens if I add a new type of LiDAR? How does that allow me to get more productive or get me a higher quality product than what I already have today? A quick introduction to Mirabilis design. We've been around since 2003. We're a Sunnyvale, California-based company. And as I mentioned earlier, our goal is timing-based system analysis. We'll actually take the model-based system analysis concept and move it one step further, which is incorporate timing and power consumption into the particular design. We're a global company, have customers worldwide, and you can see a variety of products that are built using Visual Sims. Kind of gives you a good idea of the types of products that we've been associated with for a number of years. The product is called Visual Sim, and Visual Sim is a graphical modeling and simulation software. There are two key things in Visual Sim. First and foremost is you can define your entire system. So your electronics, your software, your system can be described within Visual Sim. The second aspect is the extremely fast, rapid prototyping, which the reason for the speed of modeling is because of the large number of libraries that are already pre-built and available in the environment, allows you to assemble up a system very quickly. Now, in most of today's systems, there's a variety of C code that's already available. There is like pre-existing simulators. And of course, a lot of data is maintained in Excel or in traces. So the tool has interfaces to be able to import them quickly and use it within a Monte Carlo simulation. Now, another key aspect of this digital twin using Visual Sim is the variety of analysis. So you can start off with the functional analysis where You're looking at the flows, you're looking at what the scheduling needs to be. From there, you start looking at performance, which is more timing related, throughput related. And at the same time, also look at the power and do a power timing trade-off. And of course, one of the things that we try to do with a lot of our designs is doing a overlay, a failure overlay. So to give you an idea of what that means is I've got a design, which in this case has got a network, and there are two sensors that feed data into this subsystem right over here. It's got the hardware, it's got the real-time environment, and this is the operating system of choice. In this case, it's called AutoSAR. But what I also do to the model is I can add these variety of failures that I can describe. So, for example, I can do some spurious analysis. I can modify the table with a different value in it. I can do those kind of things. So really, is my system capturing some of those errors? Are you able to capture those errors? So if I run the simulation, we're really going to focus on this one over here. So you notice how it's very symmetrical. What I'm going to do is I'm going to turn on the false. Now realize that in this case we only have two sets of false, but in a real system we would have a much larger set of false that would be injected into the particular design. Now, two things that we want to focus on. First one is notice here how it is very symmetrical. Now it's out of sync and it doesn't even show up here. That's one. The second thing that is very interesting is the concept of not just looking at an analytical model and saying that, yep, these are the worst case execution time, so we should design for that one. But rather what we're looking at is what's your execution time requirements and seeing if, what are the technologies that fit in to that time space. So allows you, for example, to look at this and see if anyone's struck over the deadline max. It gives you an idea of where system bottlenecks can be. It kind of gives you your visibility into what exactly is the internal operation of this particular system. Now, going back to our presentations, I mentioned it's performance, power, functional, and failure. And you can incorporate electronic software and systems into the same design. Now, this one here is a list of all the different IPs. We add about 2 IPs a month in a variety of market segments. So one day it might be 5G, another day it might be automotive, third day can be aerospace, space, defense, semiconductors. So every month is a different product that's launched. Now, some of the key aspects here are on the way left here, you see the traffic. This is what allows you to generate like network activity or requests coming in or an interrupt coming in from a MEMS device that you can model either based on a distribution or on a trace file input. The other aspect is the queuing here. Using this, you can pretty much define any system level component, be it mechanical, electrical, electronics, any of those kind of things. And then, of course, you got a variety of board level, network level, software, all of those kind of things that can also be incorporated into the same model. So what this allows you to do is allows you to create a digital twin or a virtual prototype of your entire system, and then incorporate things like your photovoltaic cells, your nuclear cell, batteries, and then try to see by using a combination of these listeners, what is my performance? Is there a degradation of my performance when I make certain changes or going from one vendor to another vendor, or is there more of like a significant performance improvement as a result of doing these kind of things? So it's really about trying to evaluate which one is the best option based on the digital twin or the virtual prototype. Now, one of the things that also comes with the system level modeling IP is a large number of visualization of this design. Now, visualization traditionally has been that you send some data in and it gives you results. The big difference here is one is it's dynamic. The other is that you can get results that can compete, can work across each other. So to give you an idea of what that means, when I ran the simulation, you saw the plots being generated in real time. So that's one type of analysis along with the reports. Another type of analysis is where we get offline recording. And so here, for example, I can see what the range of buffer occupancy is for the different devices in my system. The other one can be that I'm looking at traffic rates as I keep changing the traffic rate. How does my delay? How does that delay, change? So, for example, over here, you can notice, irrespective of the traffic rate changes, the delay doesn't really get affected across these subsystems. So, if you look at the green one, which is a bus and it's got the highest latency, it doesn't really change that much when you go from like one type of design to another type. So this is something that, I'm sorry, when you go from one traffic rate to another traffic rate in terms of your user requests. What you can also do with these is you can also get more interesting comparative analysis where you're looking at the buffer occupancy versus the total delay. It gives you, that kind of analysis as well that you can try to utilize to figure out exactly what is happening in your design, trying to be able to identify where your bottleneck is. So for example, when I look at my utilization, you can see right here, this is the processor, the CPU1, and you can see it's got not only the highest delay, but also has the highest utilization when you look at the colors. While right down here, the lowest delay ends up having the lowest utilization, which is kind of an interesting phenomenon that you can utilize to make decisions on your specification. Now, what are the biggest design challenges that motivate you to create an early prototype, which is the digital twin? First and foremost is unpredictability. One of the problems in today's systems is that there are so many different combinations of topologies, so many different vendor products, that it's very, very difficult to be able to analytically or using a spreadsheet or paper and pen, it's very difficult to be able to predict exactly what will be the timing, exactly what will be the flow, being able to capture all of that kind of information. And the reason being is that if you have so many different applications spread across a distributed system, and whether it's on a system on chip or whether it's in an industrial power plant, and you have to schedule all your software tasks across all of these particular designs. Now, that is the first piece of it. The second piece of it is really the software architecture. As I mentioned earlier, the software is what's controlling your entire system as everything moves over to electrical electronics. So you have to look at, what's the impact if I change the priority, change the offset, if the response time changes. How does that impact my ability of my electronics to be able to trigger the MEMS or the mechanical system or things like that? The third piece of it, and this is probably the most interesting piece for most engineers, is really about innovation. For example, I've got avionics. How do I introduce artificial intelligence to it? I'm doing a car network. How do I ensure cybersecurity on my gateway? I've, creating a base station for 5G. How much of power is that being consumed? So allows me to evaluate all of these different options and identify all the unknowns. So that way, I have a complete design solution by taking into consideration all the different subcomponents or even exterior to create one global design. Now, going back to what we were talking about, the scheduling and the unpredictability, one of the reasons is that now there's a lot of concurrent software execution. What that means is that you have all these subsystems, they're all connected together, and then you have data-dependent behavior, so you have a sequence of tasks. Each one gets mapped to a subsystem. And then, you have some sequence of flows. Having a single application makes it fairly easy to compare, determine your scheduling, how much of resource consumption is there. The challenge is that today's systems try to leverage, highly distributed systems try to leverage sharing across a number of subsystems. So for example, when I create a new set of tasks and I map that to the platform, and then I start incorporating the flows within that, my use cases, you can see now it's getting a little more difficult to be able to predict what is the overlap of activity across all the different subsystems. So scheduling becomes much more difficult. You're going to have corner cases, anomalies that you have to cater to. Now, when I look at this particular design, which I'm actually going to move into the tool itself so we can look at it. And I'm going to bring up that particular model because it's kind of an interesting model of what is possible. I'm just going to bring up that particular design. So this one here is the same model that I showed you. I've got the CPU 1, 2, DSP-IO, bus bridge, and bus 2. And I've got two different use cases that are being scheduled on this particular design. Initially, I keep these at 400 megahertz, and I'm going to go ahead and run the simulation. And what we're looking at is the latency right over here, the ones of interest, which is about 1.6 microseconds, and it starts at about 1.0. I'm going to actually put some dots here so we can actually see it better. So you can see where the range of latencies are. I'm going to then take one of these buses and downgrade them to a 200 megahertz bus. And I want to see what happens to the entire design. One of the things that gets interesting is that when I went from like the 400 megahertz to 200 megahertz, notice earlier on I was at a max of 1.56 microseconds. Now my max is 1.45. So going to a lower speed processor actually reduces my response time. So it's kind of counterintuitive. So a lot of the analysis that you can do to try to determine what's going on, for example, is looking at the buffer occupancy versus the delay. So what this gives me is it gives me an idea of, if I add buffers to my system or reduce the number of buffers, how does that change the behavior of my overall design? So using all the visualization allows you to quickly predict what is happening in your particular design or in your particular system that you're currently evaluating. Now, one of the challenges that arises now that everything is turning electronics is being able to predict the unpredictable, which is the fundamental characteristic of my particular system, which is looking at, for example, how am I scheduling my design, in terms of the different tasks, and what is the arrival date of the data, video, voice, any combination of traffic, and then looking at what is the response time it takes in terms of the deadline. Is it being able to meet the deadline when I go power, latency, and reliability across a three-dimensional chart? One of the things to get a feel for the software architecture is that you really have to think global, not just the electronics, not just the software, not just the MIPS, not just the network, but rather the entire end-to-end system needs to be captured, and then look for power, performance, and reliability as your baseline, and then you can add other kinds of analysis tools and things like that to make your system more robust. Now, going back to the UAV model that we had, we bring up this concept of a model-based system analysis process. So what happens today in most of these model-based system analysis is that you tend to have a flow diagram with a use case using UML or SysML, And then you run a variety of formal analysis on it to try to gauge where my bottlenecks are going to be in terms of the functionality. What Visual Sim with Digital Twin takes is a new approach, which is we take the incorporate timing and power consumption and other queuing attributes directly into every single module. So when it runs along, we know exactly how much time it takes for processing, how much time is the wait state, how much time is it doing for the preparation, all of that kind of information. The reason that becomes critical is when you get started, you're looking purely at the functional aspect of my system. So I'm looking in this particular case, it's an inertial sensing system. So when I go inside of the inertial sensing system, you will see that it's got all the flows from the sensors to the attenuators. So anything from gimbals to gyros to accelerometers to sensors, all of them are captured within the subsystem. So when I go ahead and run it, my goal here is twofold. One is to figure out what my latency is for my particular design. And the second thing is to try to find out if the traces are working correctly, which is the functional flow. Starts off with the desired temperature, goes through the sequence before it's finally done with an accelerometer. Same thing right here, you can see with the gimbal motor as well, and try to understand what the bottleneck is. Where is the problem? Where is the system not able to achieve its required threshold? So once I've understood the functional aspect of my design, I now move into something that's a little more detailed. And this one is my same inertial sensing system. The only difference now is that I have replaced it with addition of resources. So all the accelerometer components inside get mapped to the accelerometer resource. Same thing with the gyro or the sensor or the desired temperature. The whole goal here is to look at the resource efficiency of my particular design. So if I go ahead and run this, you get a variety of statistics. They can be power related, or they can be end-to-end latency on each of the designs. Now, one of the things that's interesting here, and I'm going to spend a minute on this one, is the fact that if you look at like the gimbal data structure, that one has a pretty smooth flow. Even the accelerometer and the gyro, yep, it drops once, but then it's about in a very small range. The gimbal policy is constantly going up, which indicates that it's doing it's buffering or it's queuing within one of the subsystems that we're looking at. So this allows me to debug exactly what is happening within my particular design and making sure that everything is working correctly. Now, as I mentioned, if there are any questions, feel free to ask them in the chat box on the left-hand side. So that way one of our engineers can help answer a lot of those questions. Okay, so with that, I'm going to go ahead and move forward. So before we go too deep into the details of more examples with digital twin, let us take a step up and try to understand what exactly can you get out of a digital twin. So it's really about architecture exploration, which is you're trying to get the requirements and then seeing the specification matches with the requirements, or how far apart are we, and what do we need to do to get to a more accurate representation. So some of the areas you might be looking at is, depending on the type of project, cost may be important, power consumption may be important, or just raw performance could be important. But it has to include globally the entire system, and only then you can expect to get good quality metrics about my particular design. Of course, there's performance, power, and functional correctness. So if you look at this one here, this is a jet engine controller. You have the I/O card, which has all the different sensors connected to it. You have the basic backbone, and then you have an attenuator on the other side, which hopefully he's taking the content over to a recycling environment where he can hand it off to them after every single surgery. Now, beyond the basics of architecture exploration, which is power, performance, and functionality, there's a variety of other types of analysis that you can look at. So you can look at, for the main thing being resource efficiency. Can be at the processor, or it can just be how efficient is the DMA used to be able to go access the MEMS device. So when the MEM is requesting or is ready, there must be data that's being fed in. Now, all of these come in at a cost. So, for example, many cases we've had to add redundancy. There is, the test of the failure modes by creating a more reliable, robust system. And of course, the big thing today is cybersecurity. Incorporating, say, the cybersecurity on top of the gateway, what kind of overhead does it cause in terms of the effective throughput that I get? Now, let's spend a few seconds talking about the benefit of such a design process. The reason that the digital twin is so successful and has been incorporated in many hundreds of projects is the fact that you get to know everything about your design extremely early in the product life cycle, even within the first couple of months. One of the reasons being is that you can accelerate the model to create the digital twin or the virtual representation fairly quickly. Now, as a result of doing that, you identify all your faults and your bugs and your corner cases and your test cases and things like that. So what happens is you're not running your development and then finding a bug, but rather you're running your development after you find all the bugs and after you completely clear out the design. What does that mean? It obviously means into huge amount of savings in terms of product schedule or the project schedule. The average, now one of the things is you can look at it two ways. You can look at the average gain for in terms of how much of time you save, but you can also look at the revenue recognition, which is either you get the revenue a little earlier, or you have a better revenue mark because you come in at a lower price point. Another side benefit of this is really where you have the ability to provide extremely early data, even before you started developing, extremely early data to like the FAA or the National Highway Transportation Board, things like that, on some new technology or some new capabilities that you have developed, so that they're already in tune when you go in there for your final approvals. Now that we've seen a little more about the digital twin, understanding what the digital twin is all about, let us take it through and try to understand how can this digital twin be applied in a real environment. So we're going to take two systems. One is going to be a payload, a space payload, and the other one is going to be an industrial application, which is a power plant. So we're going to compare the two and try to see how the digital twin helps out in both those environments. We have time during this engagement. We're also going to look at a subsystem, in this case, an inertial navigation subsystem, and trying to see how the flow diagram helps you to come up with, build up a methodology that eventually helps you get to implementation. Now, one of the things that you start off with in a digital twin is really a block diagram. So this is what my overall CubeSat design is ready. The second aspect of it is what is your requirement? Is it the response time for a particular task? Is it the cost? What aspects are important to meet my performance, to meet my system behavior or my system performance? So that's really what we're trying to target with the design. Now, what you can do is from there, you can create a use case by defining or converting what the actual operation is going to be in the system into some sort of a Excel or a CSV or into a task graph that you can use to describe. So in this particular case, we've got the description of how the constellation and the orbit are being scheduled. So you can see, you got to wrap up the image, the tactical download, the TTCs, and you can also see during the orbit at what time do they start, how long they take. You can look at all of those kind of things. Once you combine all of these, the next step is for you to assemble up the particular design. So what you're seeing over here is all the subsystems, the battery, the PV cell, and then of course you got like the definition tables and the scheduling. Now, one of the key things in Visual Sim is that we have twofold. One is where you use off-the-shelf components to create models. The second one is where you have either your own proprietary designs or you have your own kind of thing where you've taken multiple vendor products and assemble them up together. So how do you create those? So for those, Visual Sim with the digital twin has its own custom development environment, allows you to very easily either import a model or construct a model using our script language. So it allows you flexibility in terms of both looking at what the system is going to be doing and understanding how it's doing it, and the ability to very quickly or rapidly prototype your particular design using pre-built building blocks or the custom development environment. Now moving over to the design from here. Now, this is the digital twin associated with the CubeSat. You can see all the subsystems, the battery and the PV cell I mentioned earlier. But right down here is where the interesting part of the design is. First and foremost is what are the different orbits we're interested in seeing. So for example, I have 0 to 250. You can see all the task IDs over here. And each one of these orbits have a different set of tasks. Over here, you see the latency to complete each of the time it takes, maximum time it can take to complete each one of the tasks. And this one here is the most interesting, which is twofold. First is the fact that, for each one of the tasks, which subsystems are turned on, and what was the charge, that is, how much of charging is happening when it's facing the sun versus it's in eclipse. The other piece of it is being able to do the processing. So, when it's an eclipse, the battery's life is short. In those kind of situations, you may want to shut down certain systems or put it into low power mode, things like that. So, allows you to understand using this use case or using a trace file, figure out what the input attributes is to the particular design. So now when I go ahead and run this, you get a variety of statistics out of the particular design. Some of these are related to what is the latency to complete these different tasks within the system. Another one is looking at the peak power consumption over the period of these orbits. So allows you to be able to figure out exactly how my orbits are going to behave even before I've had a chance to build anything. So you can see, for example, this is the power consumption. This one is showing me the activity related to the particular subsystem. You can see what's happening here. You can see what your latencies are. You can see when my subsystems were active over time. Gives you all of that kind of visibility into my design. So what you have here now is the ability to be able to visualize what your system can do while you're actually studying or analyzing it before you even start going and doing development. This is on a CubeSat or a satellite payload. Another one which is completely different. The difference being is that the first one is a highly integrated system. It runs on battery. What you're very concerned about is all the flows are correct. The second one here is is more of an highly distributed system, runs on a power socket, has got networks, things like that. When I look at this particular subsystem, it looks fairly different in the sense that I got a primary and a standby PLC. I've got an energy supervision, but I also have all the IOs that connect to all the sensors, but also have an Ethernet interface to connect back to both of these primary and standby PLCs. Now, when I look at the system model, which I'm going to open up right now, this is the design over here. As you can see, I've got a primary and I have a secondary system. And what I'm going to do is, the plan is I'm going to keep running this, and I get a failure on one of those. Then what ends up happening, and I'm going to turn off the failure for now, is that it's going to flip over to the other module. And what I want to see is whether I still maintain the same MIPS that I was originally targeting. So a variety of statistics is what we're generating. We're generating latencies on these IO devices, on these other subsystems. But the main one is the MIPS over here, which is how effectively I'm using this primary and secondary PLC. Now, you can see what the range of the MIPS are. So it's about 400 megahertz. So we're running about 1 gigahertz processor, and we're getting about a max of about 400 megahertz, so between 200 and 400, or possibly 450. It's kind of where our range of the efficiency, or about 40% efficiency on my processing device, or my PLC. These show me what my latencies are associated with that particular design. Now, when I take a look at this design, there's a few different things. One is obviously the IO devices, and you can see there's the the different sensors, and that one is my device that's the polling device that's accepting all the data and then deciding to send it onto the network. The one that's most interesting is obviously the primary processing unit. In this particular case, this is the the Schneider Electric Modicon M580 product that we modeled. And what you're seeing over here is these are the use cases, and that's the hardware platform within that particular subsystem or component. So you have the thing coming in through the network, goes up to the mapper here, which then maps it over to the processor on my hardware board. So one of the things that happens is that the use case is really separated out from the hardware platform. The second thing is, when I run the simulations, I believe I already did. Yeah, you saw all of the different things. So one of the key things that you can do with the digital divide or the digital twin is the ability for you to create completely custom views, completely custom visualization by setting up these assertions or setting up these conditions to decide what gets plot or what gets plot against who, things like that. So it becomes a much more visual communication about what exactly your particular design is doing right now with the use cases and the traffic that have been applied to it. As I mentioned earlier, if you have any questions, please do put those questions on the chat window. I'm going to take a quick break because I've been getting a few more questions. Okay. As you can see, these were the subsystems. There's the mapping to the processor. There's the node interface, and these are all the sensors on the IO backplane. So it allows me to be able to study my overall design. Now, one of the key things that we want to do as part of any sort of methodology is to really start at a functional level and then work ourselves through a resource modeling, more detailed hardware software modeling, and then finally, like hand it off to someone to go ahead and implement it. So on the functional side, what is very important is to be able to accurately capture all the different flows from the sensors to the attenuators. So if I look at the design that I will be discussing today. Oh, oops. Here we go. So what you see over here is we've got all the peripherals, all the computer software, you got the CPU, you got a controller right here, which is receiving their request from an external events, and then that's triggering off these different peripherals and the processor themselves. Now, these are, one is the work stack, which is telling it, how much, what needs to be done and when it needs to be done and how many resources are required. The second one is a command station, which is really about, specifying what that particular robot is doing. So here, what you're looking at is really a robot that goes in and sweeps and cleans a nuclear power plant. So the command tells me, is it like going in and docking or actually getting out there and starting to do the cleanup work. So when I go ahead and run the simulation, uh, the main focus here is we're trying to see if we can maximize the load here, or we can maximize the amount of activity that is done down here at the CPU. The reason that that's important is because what we're trying to do in this particular case is we're making a robot, which means I would much rather have it have like a single processing unit as opposed to a distributed processing unit. One is because of space limitations, but other things is because of cost conditions where the system will start there, the weight will start increasing, being considerate of all of those kind of attributes. So with this, I would like to wrap up this webinar on creating a digital twin for product definition. I'm going to open this out to questions. Anybody has any questions or is interested in a particular application area that I haven't covered, feel free to go ahead and answer those questions. Or, I'm sorry, go ahead and ask the questions. I'll try to attempt to answer those.